Now let's consider an example where we have a dynamic hazard, and let's see how we can identify the possibility of the dynamic hazard occurring and how we can address this dynamic hazard, meaning how we can remove it. So let's take a function that is deceptively simple at first, but we will find that this is a very problematic function. It's a plus b bar into b plus c plus bd plus e. So when we talked about static hazards, we saw two approaches towards solving them, either using Carnot maps or using just Boolean logic. Now, using Carnot maps is limited and limiting because it only works for functions with a small number of input variables. The K-map approach is also not feasible for dynamic hazards, so we have to look at ways using analysis, using algebra to deal with this. When we talked about static hazards, we said that the possibility of a static hazard occurring happens only when a variable makes more than one appearance in a function, and when one of these appearances at least is the inverted form and one is the true form. So if a variable doesn't make more than one appearance, there's no cause for concern about it in terms of hazards, and even if it makes multiple appearances but they are not inverted forms, then also there's no cause for concern. Now, when we look here, we find, for example, that A, C, D, and E do not make multiple appearances. Each of them makes a single appearance at the output. So A, C, D, and E are not sources of hazards, either dynamic or static. B, on the other hand, is a possible source of hazards because it makes more than one appearance, and one of them is inverted, the others are not inverted. So there's a possibility of static hazards occurring here. Now, the same logic can also be applied to dynamic hazards. A dynamic hazard is possibly going to be present in a circuit if a variable makes 3 appearances. So it doesn't have to be 2 appearances. In this case, it has to be 3 appearances. And if these 3 appearances have a true and an inverted form. So in this case, B does make 3 appearances. So B could actually cause static hazards or it cause dynamic hazards. What we're looking for is structures of the form B, B bar, or B plus B bar, or B into B plus B bar, or BB bar plus B. So any of these is going to cause a hazard to occur. The first is going to cause a static 0 hazard. The second is going to cause a static 1 hazard. The third is going to cause a dynamic 1 to 0 hazard, and the third is going to cause a dynamic 0 to 1 hazard. So we have to figure out which of these could actually result from the function above. So as we did with the static hazards, we have to look for ways to bring out these 4 structures from the function above, and this happens by forcing the other variables to have specific values. So, for example, if the value of A is equal to 0, this allows the first B bar to become observable. And if the value of C is equal to 0, this allows the second B to be observable. If the value of D is equal to 1, this allows the third B to be observable. And if the value of E is equal to 0, then the entire function is observable. So with these inputs for the 4 other input variables, the function f will have the form B bar B plus B. So this is a structure that is obviously connected to 0, 1 dynamic hazards. And so there will be a 0 to 1 dynamic hazard if B makes a transition while the 4 other inputs have these specific values. If any of the other input variables have other values, you will not observe the dynamic hazard. For example, if E is equal to 1, then E is masking the entire function. The entire function has a value of 1. If A is equal to 1, then the first B bar is not actually going to be able to make it out, because, and in that case, the function is going to be equal to b. So only for this input combination of a, c, d, and e would we observe this form of b, which can result in a dynamic hazard. Does it necessarily result in a dynamic hazard? It really doesn't. It doesn't necessarily result in a dynamic hazard. It depends on the differential delays of this b and these two b and b bar. Specifically, this b has to be delayed, and it has to be delayed more than this product, and this product has to produce a static hazard. Now, here's something a little bit confusing. This function actually has other possible hazards. It specifically has two static hazards related to the input b. It could have a static 0 hazard or a static 1 hazard related to b. And these two hazards are completely distinct and independent from the dynamic hazard, and they have to be addressed separately. This might seem a little bit confusing at first, but just bear with me. Now, let's consider a situation where the other input variables, a, c, d, and e, have slightly different values from the values we just considered here. For example, let's consider the situation where a is still equal to 0, d is still equal to 1, and b is still equal to 0, but c is equal to 1 in this case. So the only difference is that c is equal to 1. So in this case, f is equal to b bar, because a is still equal to 0, but c is now equal to 1, so it just reduces this entire bracket into 1. And in this case, d is equal to 1, which means that this b makes it out, and e is equal to 0. So in that case, f has the value, has the expression f equal to b plus b bar. This obviously shows us that we have a static 1 hazard, or at least the possibility of a static 1 hazard. Now, let's consider another situation. Again, A, C, D, and E are going to be slightly different from the original case here. So in this case, A is equal to 0, C is equal to 0, and D is equal to 0, but D is also equal to 0. So they're all equal to 0. In that case, F is going to be equal to B dot B bar. This is a static 0 hazard, and it will occur for these input values. One might actually protest, and one might have a good reason to protest, that these two hazards are part of the dynamic hazard. After all, the dynamic hazard is formed by the basically the addition or the amalgamation of these two expressions, because the dynamic hazard is when we have b times b bar plus b. So it's basically this part plus this part. So yeah, I mean, we also talked about in the anatomy of dynamic hazards, we talked about how a dynamic hazard has to have an underlying static hazard. So yeah, it does make sense. However, these two hazards are still independent hazards. They have to be there for the dynamic hazard to make it out, but addressing the dynamic hazard would not address these two static hazards, simply because they occur for different input combinations of the other variables. So if you address this dynamic hazard, it will not address these two static hazards because they make it out under different circumstances. To better understand this, we have to discuss how is it that we address dynamic hazards, and how is it that we address static hazards. So because we already know how to address static hazards, let's do that first. So let's take the static 0 hazard, for example. This static 0 hazard occurs when A, C, D, and E are all equal to 0. In that case, the function f is equal to b dot b bar, which is supposed to simplify down to 0, but it doesn't because of differential delay. The way we address this is we multiply the original expression of the function f by a new bracket, a new term, which in circuit terms is going to be equal to adding a new product term by adding an OR gate and then an AND gate. This product term is going to be active only when we have all the combo of the other, we shouldn't be writing b here. So all the combo of the other variables a, c, d, and e be equal to 0. So when a, c, d, and e are equal to 0, this bracket is equal to 0, and it forces the value of f1 to be 0, regardless of the value of b. Now, for any other combo of a, c, d, and e, this bracket is equal to 1, and f1 will be equal to f. So we have two cases. For a, c, d, and e all equal to 0, f1 is going to be forced down to 0, not by b, but by this bracket. This allows us to mask the glitch, right? But for any other case, for all other combos of a, c, d, and e, f1 is equal to f. Now, this means that we have solved the static hazard without changing the function, because the function is the same. And right here, the function is forced to 0. This forcing to 0 does not change the function, because the function is supposed to be 0 if b is equal to 1 or if b is equal to 0, which means that it is always 0 for this combo of a, c, d, and e. So just by simply multiplying by this bracket, we have solved this static hazard. Now let's take the static one hazard, which occurs when a is equal to 0, e is also equal to 0, c and d are both equal to 1. So this occurs because in that case, the function f is equal to b plus b bar, which is supposed to simplify down to 1. It doesn't, though, because of the differential delay of b bar relative to b. So the way to deal with this is to add a new term, in this case, not multiply by a new term. That term is equal to 1 for this input combo of a, c, d, and e. So we have to add the term a bar, c, d, e bar. This term is equal to 1 for this input combo of a, c, d, and e, is equal to 0 for all other combos. So in this case, we'll have f2 is equal to f plus a bar, c, d, e bar, right? And this is going to solve the static one hazard, because this term is going to force the function to be equal to 1 regardless of the value of b. And it doesn't change the function, because for any other combo of a, c, d, and e, f2 is going to reduce back down to f. Now, to solve both static hazards, we have to have f3, which is equal to f, multiplied by the bracket a plus c plus d plus e, and then with the additional product term a, c, d, a bar, c, d, e bar added. It doesn't matter if you add this term first or you multiply by this bracket first. It solves the problem in both cases. Now, it's important to understand that when you use these additional terms, they're going to mask the static hazard, but they are not going to erase the dynamic hazard. This might not be immediately obvious, but it's actually not that hard to see. Now, the dynamic hazard, as you can see here, occurs because of the expression b bar b plus b appearing at the output of the function. Now, we should object by saying, well, we have already actually masked b bar. This part of the thing has been masked. So if we have masked this underlying static hazard, we shouldn't actually observe the dynamic hazard under any circumstances, right? Because one of the conditions for a dynamic hazard to make it to an output is for there to be a static hazard that manages to make it to the output. So if this static hazard doesn't even exist anymore, the dynamic hazard shouldn't actually exist. And the answer, well, you did mask this static hazard, but you only masked it for this input combo of A, C, D, and E, which is not the input combo that causes or triggers the dynamic hazard. So for any other input combo of A, C, D, and E, this product term is equal to 0, and it does nothing. For any other combination of A, C, D, and E, this sum term is equal to 1, and it does nothing. So for this input combo, which is neither of these, this form still makes it out to the output, and the dynamic hazard still occurs. So it's pretty obvious. To remove the dynamic hazard, we need to add a new term that actually removes the hazard for this input combo of A, C, D, and E. So as we did for the static hazards, we have to do for the dynamic hazard, except by taking care to do this for this input combo. There's a problem here, however. If you form a product term out of this input combo, meaning A bar, C bar, D, E bar, and then add it to the original function, or if you form a product term A plus C plus D bar plus E, and you multiply it by the original function, this actually changes the function. So this changes f. This does not equal f. Now this is a problem because when we added these additional terms here or multiplied by them, we still didn't change the original function. This was still equal to f, and this was still equal to f. And that's a precondition, right? We don't want to solve the hazard and at the same time change the function. That's not a good solution. That's not a correct solution. And the reason that this happens is you're trying to remove the dynamic hazard as if it's a static hazard, which is not true. What you need to do is you need to suppress this term, this underlying static hazard, the B times B bar, for this input combo. So the idea that you need to suppress the underlying static hazard is correct. The problem is you were trying to suppress it for a different input combo. So this is an underlying static zero hazard, and the way to suppress it is by multiplying by a bracket term. So as we did here for this static zero hazard, we need to multiply by a bracket term. So to begin with, we need to multiply by a bracket term. However, multiplying by this bracket term is going to change the function. And the answer is you don't actually need to multiply the entire function by the bracket term. What you need to do is you need to multiply the underlying static hazard, meaning you need to only multiply the B times B bar expression by the static hazard, meaning that you only need to multiply the brackets that originally had the B dot B bar in the original function. So if you go back to the original function, this original function consisted of two parts, basically, the product of these two brackets and then these two sum terms. And what you need to do is you need to multiply by this bracket right here. So you need to have A plus C plus D bar plus E right here. You don't multiply the entire function by it. You multiply the part that contains the underlying static hazard. If you do that, you're not going to change the entire function. You'll find that multiplying by this bracket doesn't actually change the expression of the function. If you expand it and you do a simplification, you will end up with the original function. Whereas on the other hand, if you had tried to multiply outside right here, you would have changed the function. And so in this case, you will solve the dynamic hazard because basically this bracket is masking the B dot B bar term. And so you don't actually have an F equal to B dot B bar when you have this input combo. What you have is F equal B times B bar into A plus C plus D bar plus E plus B. Now this bracket for this input is going to be equal to 0. And in this case, it's going to suppress this entire term down to 0. And so F is going to be equal to B, and you will see the transition without any glitching. And it doesn't change the function because all it does is it reduces these two first brackets to 0 under a very specific circumstance. Now, one valid argument here is that if we multiply by this bracket, if we multiply this initial or first product term by this bracket, doesn't it also automatically solve the static zero hazard, this hazard? Because you have removed that, right? The answer is no. You still have to address this independently by multiplying by this final term because this static hazard appears for this input combo, whereas this bracket is active for this input combo. And so you need to do both independently. And so to summarize, when you look at the function, you try to observe which logic values, which logic variables have more than one appearance. If they make two appearances, then there's a possibility for a static hazard. Of course, these two appearances have to be in true and complement form. if they make 3 appearances, there's a possibility for a dynamic hazard. You try to then extract one of these 4 forms, and if you can extract more than one of them, you have to extract all of them because each of them represents a different kind of hazard. Now, for each of these, you observe which input combo of the other variables causes this form to appear at the output, and that's the input combo that you are worried about. For static hazards, you will end up multiplying by a final bracket or adding a final sum term to remove the static hazard. For the dynamic hazard, you multiply or add by an internal bracket in order to remove the underlying static hazard. If you remove the underlying static hazard for the dynamic hazard, that doesn't mean you have removed the static hazard because the static hazard exists independently.